In this video, we're going to talk about the partial fraction method using Laplace transform techniques. When you do Laplace transform techniques, we do it slightly differently. So we can talk about that later. And then we also do about 20 problems there. So the partial fraction method is very important when you try to do the inverse Laplace transform. That's when we're going to use that inverse Laplace transform. And also, the way we do it here is different, slightly different in certain cases, not every time, certain cases than the standard partial fraction technique. So we're going to see when this is going to change. So we're going to go different types one by one. So let's start with the most common one is the division. So let's start with the first problem. Say we have s plus 5 over s plus 2. So if you have something like that, what we can do is we can use a simple algebra trick here. So the goal is to recreate the bottom term in the numerator. So what we're going to do, we're going to write that numerator like this. We can write s plus 2 first, because that's the denominator term. And then we can adjust the other term. So you can see we have s plus 2, we have 5 here, that means we have a 3 as a leftover. And then divided by s plus 2. Now what we can do, we can split them. We can write this one as two fractions. We can write first one as s plus 2 over s plus 2. That's the first one. And then we have 3 over s plus 2. So that means finally your answer is going to be 1 plus 3 over s plus 2. So that is how we can rewrite something like that. So just using simple algebra. And also, like, you can get the same answer by using a long division. So you can use a long division. So use the long division. So let's see how we can do that. It will be useful later. So long division. So what we can do, we can have s plus 5. So we can divide this one by s plus 2. And when you divide by s plus 2, and you can see that there's a 1 of them. So we have 1. And when you multiply by 1, you're going to get s plus 2. And then what we do next is we're going to subtract them. When you subtract, what we normally do is we're going to change the sign of the bottom one and add. So if you do that, you get 3 as the remainder. So that means you can write this division problem like this. So when you divide s plus 5 with s plus 2, you get 1 as the quotient, that's that one. And then how you write the rest? You get a 3 as a remainder. You also need to write the divisor here. And that's how you write the answer. And you can see this is exactly matched with the previous answer. So same thing. So you can also get the answer using the long division. And also I would like to discuss the synthetic division for this problem. So we can also use the synthetic division, synthetic division. And when you do that, we only worry about the coefficients. So how we write this problem? So it is s plus 5. S plus 5 you can write as 1 and 5, because those are the coefficients. And then what we do, we write it the other way. We write it like that. So exactly the opposite. And then we need to write the 0. So s plus 2 means the 0 is negative 2. So if it has plus 2, so the 0 is actually negative 2. And then what we do, so that's what you write first. You write the 0. And then we're going to copy this number down. So this 1, you rewrite it. And then we're going to multiply by this number. And we're going to add that number here. So when you multiply by negative 2 with 1 and you add, you get negative 2. And you can see when you, now we add them. So we add them down. So when you add, and you can see you get 3. So this is actually going to give you all the coefficients. So what this means is when you divide s plus 5 with s plus 2, because you put the 0 there, you get 1 as the quotient, just 1 plus same thing. and then this is the remainder, so it's 3, so it's 3 over s plus 2. So you get the same answer using all three methods. So you can use any of those methods to get the answer when you have a division like that. So let's do another problem. So as the next one, we have s plus 2 over s plus 5. So this is the same problem but upside down. So what will happen here is same argument. We're going to recreate the denominator and the numerator. So that means we're going to int 5. So we have s plus 5. So what you want to do is to cancel this, because you just add a 5. You can't just add a 5. So what you want to do is you have to cancel this 5. That means you're going to subtract 5. So that means you can write this one as you're going to get, so we have a 2 here already, but you have to subtract 5. And then over s plus 5. And you can see that you can simplify this one as s plus 5. And then minus 3 over s plus 5. And if you do the simplification as before, you get a 1 minus 3 over s plus 5. So you can write the answer like that. You don't write all those steps, but I'm just writing all the steps just to explain what's going on here. So again, what was the argument? You're going to recreate the denominator in the numerator. That's how we do. Okay, so let's do another one. So let's do next one. So say we have s squared or s squared plus 3. So it'll be a very similar argument. So we can write this one as so same thing. So s squared, we're going to recreate the numerator, the denominator in the numerator, and then you subtract 3. So that they cancel, 3 and 3 cancel out, and then s squared plus 3. Now again we split them. So when you split, you get 1 minus 3 over s squared plus 3. So that's what you get. And when you do the inverse Laplace transform, we will see how we can use this idea. So it's be very clear after this. Okay, so let's do the next one. So next, suppose we have s squared divided by s squared minus 4. So this problem actually, this is not like first what we do is we're going to factor the bottom and write as x minus 2, x plus 2. But we are not going to do that when you do the Laplace transform. So that's a different one. So we normally factor these two, and then we can write those factors, but we are not going to do that when you do the Laplace transform. So that is like a different one. So what to do? We do the same argument as before. So we're going to recreate the denominator. That means it's a squared minus 4 and then plus 4. And then we have a squared minus 4, and then split, you get 1 plus 4 over s squared minus 4. And we're going to stop like that. So you can see this is different from the regular partial fraction method. So this one is different from the regular partial fraction method. We are not going to factor this one, and it will be very clear when we do the actual problem. Also, like if you try to do that way, I'm going to call this as the method 2. This is what happened. So let's start with the problem. So we have squared over s squared minus 4. What we normally do is we're going to factor the bottom, not the top. So which is s minus 2, s minus 2, and then s minus 2, s plus 2. And then we can write the partial fractions here. So we can write identical to, if you write it a over s minus 2 and b over s plus 2, actually this is incorrect. This is not what you get. So be careful with that. The reason is you can see these two terms are the same. So that means the degrees are the same. Degree of the numerator equal degree of the denominator. So it's a degree of the numerator equal degree of the denominator. So when this happens, you need to do the division. So when you divide these two, just the leading coefficient, and you can see that s squared over s squared actually going to give you 1. So the correct factorization of this one would be, so it's going to be not that one, so it's going to be 1. You get 1 when you divide the 2 plus the rest. So it's a over s minus 2 plus b over s plus 2. And if you are confused with 1, you can actually just write it like this if you want. You can say, okay, A plus B over S minus 2 plus C over S plus 2. You can also write it like that and then find all A, B, C, and then you will see that A is equals to 1 if you do that. But if you can do that beforehand, if you divide those two numbers, S squared over S squared, two terms, S squared, and you see that you're going to get 1. So you can actually get there directly. And then we're going to discuss this later when you talk about those distinct linear factors. Okay, so let's look at the next one. You can also get the same answer just by the lone division. So, so what we can do is, in this case, S squared. So you can divide S squared by S squared minus 4. So you can see that you have one of them here. So you can write 1. And when you subtract, what you get is, you can see when you can multiply, what you get is S squared minus 4. Now what we can do, we're going to subtract them. When you subtract them, you see that you change the sign and add, you get a 4. So that exactly tells you what's going to happen. So that means when you divide S squared by S squared minus 4, you get a 1 and a 4 and a S squared minus 4. So you see that you get the same answer. So that's the other way to do this, just with the lone division. Now let's talk about the next main type. So first we discuss the division technique. So that's the division technique. You just divide and get the answer. So let's talk about the next one. This is what we normally call the distinct linear factor situation. So distinct linear factors, and we assume that the degree of the numerator is less than the degree of the denominator. So we're going to make the assumption degree of the numerator is less than degree of the denominator. If not, what we do, we first do the division. We do the division and get the remainder part, and then we do that. So that's what we do. Okay, so let's look at the major theory part. So what we do, we normally start with a problem like this. So let's say you have some term S plus 7 over, let's say you have S. So we for the Laplace transform we use S. So we have all the S here. So it is S minus A and then S minus B. So what we do, we can write this one as a partial fraction. So make sure that you write 3 lines here because we use the identity property. It's not 2 lines, it should be 3 lines. Because we use the property of identities, not property of equations. So it is A over S minus A plus B over S minus B. Okay, so the goal is to find A and B. So let's look at the actual problem here. Let's say we have S plus 7 over S minus 1, S minus 2. So we write this identical to A over S minus 1 plus B over S minus 2. That's what we do. We look at the distinct factors and write one for each. And then, so what we're going to do is, let's talk about the method 1. So the method 1, or this is like a standard method for this one. So what we normally do is we're going to multiply the whole equation by this factor. We're going to multiply by this on both sides. So once you do that, you will see on the left side you only get S plus 7 identical to, on the other side what will happen is you're going to cancel the one in the bottom and you get the other one. So that means for the first one you get S minus 2 because you're going to cancel out, and for the next one you get S minus 1. Now, so this is not an equation, this is an identity. So since this is an identity, you can plug in any value you want here. But we're going to be like kind of smart here. We're going to plug in special values. So for example, if you want to find A, what you're going to do, you try to make the other term 0. That's the goal. If you want to find A, try to make the other term 0. So that we could plug in S equal 1, then the other term going to go 0. So that's the argument here. So with the substitution. So we can substitute S equal 1. So when you substitute S equal 1, and you can see on the left side you get 8. Now I write equal sign. A times, if you plug in S equal 1, you get here 1 minus 2, and you can see this is going to give you A as negative 8. And the same thing, So you're going to go to the other ones, you're going to substitute. So if you want to find b, try to make the first term 0. To make the first term 0, you plug in is equal to. That's how we do. So if you do that, so you get 9 on this side, and then we get first term is 0, so you get b times, if you plug in 2, you get 2 minus 1, which is 1. So what you get is b equal 9. So you directly find a and b quickly, and then that's it. So that means you can plug in those values here. So if you go back and substitute, we normally put the negative sign in front. So we write negative 8 over s minus 1 plus 9 over s minus 2 as the partial fraction decomposition. Okay, so this is the first method, but there is also a shortcut method, what we normally call the coverup method. So let's talk about the coverup method quickly. So this is a method 2. So the second method is the coverup method, and this is how it works. So let's look at the same problem. So we have s plus 7 over s minus 1 s minus 2, which is identical to a of s minus 1 plus b of s minus 2. So if you want to find a, so what we're going to do is we're going to cover up the term what is in the denominator. So that means you can write a. So a is equals to, we look at what is on the left side, which is s plus 7 over s minus 1 s minus 2. So what we do, we're going to ignore s minus 1 term. So we're going to cut it off. We're going to cover it up. And then we're going to, for the rest of the term, we're going to plug in s equal 1, which is the 0. So we're going to plug in the 0 from here to the rest of the term. That's the cover up method. So we're going to cover up that term, what in the denominator, and for the rest of the term, you're going to plug in the 0. So that means you're going to get 1 plus 7 over 1 minus 2. So that's what you get, and you can see this is going to be negative 8. Negative 8 over 1, so which is negative 8. So that's the idea. And similarly, you can also find the other one. So let's see how to get the b. So when you want to find b, what we do, we're going to cover up. So it's s plus 7 over s minus 1, s minus 2. Now we're going to cover up s minus 2 term. So we're going to cover up this one. So for the rest of the term, now we're going to plug in s equal 2. So that means it is going to be 2 plus 7 over 2 minus 1. So that means it's going to give you 9 over 1, which is 9. So that's the idea. And you can see it's like a very simple idea, and it can save time. You can directly find the values using this coverup method. So let's look at another example. So as the next one, we have s plus 7 over s minus 1, s plus 2. So as before, we can write this one as identical to a over, the first one is s, and the second one is b over, the next one is s minus 1, and then c over s plus 2. And then what we after that, what we're going to do is we're going to multiply by this factor. So when you multiply by that factor, you're going to get s plus 7 on this side, identical to a. What you're going to get is you do not write this term, but write everything else. You write the other terms. So that means, so it's going to be s minus 1 and s plus 2. That's the first one. If you go to the b, you can see you're going to cancel. You are not going to write this term, but write everything else. So that means it is going to be s plus 2. And then if you go to the c, it's a cs, and write s minus 1. S minus 1. So that's what you get. Now what we're going to do, the idea is if you want to find a term, we're going to use a substitution technique here. So we're going to substitute. So the idea is this. Let's say you want to find a. If you want to find a, look at the other two terms and find what is common in the other two terms. And you can see s is common in the other two terms. So the goal is to make that term 0. To do that, you're going to plug in s equals 0. So that's the idea. You try to make the common term on the other term 0. So if you plug s equals 0, you can see you get 7 here, and then a, so if I can see you get negative 1 and 2, and this is going to give you a, so a is simply negative 7/2. And then we do similar argument, so and then we can substitute for to find b, and you can see the common term now is s minus 1. S minus 1 is common, so that means you're going to plug in s equal 1. When you do that, you get 8 on this side, and then b, so you get 1 times 3. So that's going to give you the value of b, which is 8/3. And similarly, you can substitute s equal negative 2. S equal negative 2 to find c. So if you do that, you get 5 on this side, and c negative 2, negative 3, and then this simplifies, and you're going to get c as 5/6. So those are the 3 values. You can get them quickly, and you can also use the cover-up method to find all those 3 values. So let's do that in a next example. So as the next one, we have 2s squared plus 3 over s cubed minus 4s. And you can see the bottom is not factored, so we do the factoring first. So you can write this one as 2s squared plus 3. If you pull s out, you can write this one as s squared minus 4. And you can see the bottom you can factor more. So you're going to get 2s squared plus 3 over s minus 2 and s plus 2 from the difference squares factoring, and we know the difference squares. So when you have a squared minus b squared, this can be factored as a minus b and a plus b. So this is like a very important tool. Okay, so now since we have different linear factors, we can write the form now. So that means it's going to be 2s squared plus 3 over, so we have s3 minus 4s. Actually, let's look at the factored form for this one because it will be clear. So we have s minus 2 and s plus 2, which is identical to as before. We can write a over s, that's the first term. There's no order, you can write any order you like. And then b over s minus 2 and then c over s plus 2. So let's use the cover-up method now. So in the cover-up method, let's say a. So what is a? So if you want to find a, it's a 2s squared plus 3, and we do not write this one when you find a. So we write the rest. So that means it is going to be s minus 2 and s plus 2. And we're going to substitute the 0, which is 0. And when you do that, you're going to get 3 in the numerator. In the bottom, you're going to get negative 2 and a 2. So which is going to give you negative 3/4. So that's the A. And we can do the similar argument for B and C. So you get this. And similarly, for C, you get this. And then if you plug in the values, you can write it like this. So we have 2s squared plus 3 over s cubed minus 4s equal negative 3/4. Negative 3/4. And then 1 over s and plus 11/8. 1 over s minus 2 and plus 11/8. 1 over s plus 2. So you can write like that. Okay, so let's look at the other case. Let's see what happens if the degree of the numerator and denominator are the same. So so the degree of the numerator equal degree of the denominator. So let's look at this problem. So let's say we have 2s squared plus 3 divided by, let's say, s squared minus s minus 6, something like that. And you notice that these two have the same degree. squared. So what happened when you do the long division, and you can see that you are going to get a 2. So we can start with that. So we can say 2, that's what you get from the long division. And then the rest. So rest, as before, you know that the bottom you can factor as s minus 3 and s plus 2. So those are not different, it's the same thing. So it is a over s minus 3 plus b over s plus 2. So that's what you get. And then so we do the same thing. So you can use the cover up method for this one. So with a is simply going to be 2s squared plus 3 divided by s plus 2, and you plug in s equal 3, and when you do that you're going to get 21 over 5th. And then b is similarly, it is 2s squared plus 3 over s minus 3. That's what you get. And then again plug in s equal negative 2. So when you do that, you will get negative 11/5. So those are the a and b values. So so you can write the final answer, which is 2 plus 21/5, 1 over s minus 3, and minus 11/5, 1 over s plus 2. So that's a partial fraction. And also, what about this one? Let's say, so the question I want to say 8 star. Can there be a problem like this? 2s cube plus 3 over s squared minus s minus 6. In a regular problem, regular partial fraction problem, this is okay, but not in when you do Laplace transform. So this cannot happen. You cannot have a because when you simplify these two, when you divide these two, you get 2s. That's not possible when you do the Laplace transforms. So you can see you cannot find the inverse Laplace transform of this one. So there's no inverse Laplace transform on this one. Because it has to be the same or less. The numerator degree has to be the same degree, or it should be degree less than that. Okay, so let's look at the next one, problem number 9. So in this one, let's start talk about what happens if the factors repeat. So repeated linear factors. So we can look at a situation like this. So let's say we have s plus 7 over s minus a, and so s minus a and s minus b squared. So if you get something like that, we know that partial fraction has to be a over s minus a plus, now there's a question. So we know that there's a term s minus b, so it should be b, because always the degree of the numerator is 1 degree less than the denominator. And then what happened here? What happened? So we know that the bottom has to be, we can write all the terms up to the highest power. Here highest power is 2, so we can write all the way. Now the question is, what you can write for the numerator? Numerator has to be degree 1 less than the denominator, but we are not going to do that. For this special case, when the term repeat, you can show that the numerator follow the same pattern as the first one, the least one. So that means you just need a constant here. And let's see why we can do that. So let's look at the next problem and see why this is the case. Why you don't want to write cs plus d. So let's look at problem number 9 now. Let's say we have s plus 3 divided by s minus 2 squared. So we can do the long regular division problem for this one. So what we try to do, we try to recreate the numerator, denominator here. So what we can do, first we can write this one as s minus 2, that's the term in the denominator, the factored version. And then what we're gonna do, you're gonna, because you subtract, so to cancel that, you're gonna add a 2, and you're going to subtract 2. So since we subtract here, so you're going to cancel that. The argument is, since you subtract, you have to add a 2 to cancel it. So that means it's going to be 5 on the other side. 3 plus 2, 5 over s minus 2 squared. So we can always do that. We can recreate the term in the denominator. Now we can split them. So when you split them, you can write this one as s minus 2 over s minus 2 squared plus 5 over s minus 2 squared. And in the first term, you can see you can simplify this one. When you simplify, you can see that this is 1 over s minus 2 plus 5 over s minus 2 squared. So you can see that they have the same pattern. So it's just a constant in both. So you do not need a so if you go there, you do not need a cs plus d term here, because you can always do this argument, and because of this argument you can see these two terms match. So it's going to be always the format of the first term. Okay, so that's the argument here. Okay, and this is how you do this problem without partial fraction. You can just directly write it, the technique. Okay, so let's do one more example with the higher term. So let's see this interesting trick here. So how about the next one? So we do a similar argument. So let's say we have 2s squared plus 3 over s minus 2 squared. So the idea is, we know the bottom term is it is s squared minus 4s plus 4. That's what happened when you distribute this. So we try to use a similar argument as before. So we try to recreate the denominator term now. So how to do that? So we can write this one as, so we can recreate. So we're going to say 2, but there's a 2 here, and then we can rewrite this term squared minus 4s plus 4. That's what you need for the bottom. Now we're going to adjust the rest of the terms. So we only have 2s squared, so that term is fine. But when you do this one, you get negative 8s. So as to cancel that, we're going to add 8s there. And then also, when you multiply the numbers, you get 8. But we only have a 3 here, so that means you need to subtract 5 to get 3. So that's what we do. So that's the adjustment we do. And then the bottom is s minus 2 squared, s minus 2 squared. So now we can split them. So you can see the top is simply s minus 2 squared. So that means when you divide, you get a 2 from the first term. In the next term, we have 8s. Again, we can do the changes to the next two terms. So we can do this one. So let's take care of that one now. So which is, we can write this one as, if you pull 8 out, you can write this one as s minus 2. That's the bottom term. So you can recreate the bottom term as in the previous example. But when you do that, you can see that you're going to get negative 12. But you can only have negative 5. That means to cancel that, so what we can do, we can add a 11 here. So then when you simplify, you get negative 5 over s minus 2. So this is like similar to previous example. So you can see you get 2, and then you get 8 over s minus 2 plus 11 over s minus 2 square. So you can directly get this one actually without using partial fraction technique. It's just a simple algebra trick, and you can get the whole fraction here. Okay, so good. And then let's try to see as the next example how we actually do this and get the actual answer. So we're gonna do it the right way, the normal way, and then we get the answer again. So we start with the same problem. So we have 2s squared plus 3 over s minus 2 squared, which you can see when you divide as before, 2s squared, and these also have a squared term here, s squared. So I mean when you divide, what you get is the first term you get is 2 plus the rest you can write as we normally do, which is a over s minus 2 and then b over s minus 2 squared. So we're going to do the regular way and see whether you can get the same answers. And then what we normally do is we're going to multiply by the factored version. So that means when you multiply you get 2s squared plus 3 identical to 2. What you get here is s minus 2 squared, and then a, you get one term here, and then b, just get b. Okay, so and then after that we can use substitutions. So we're going to substitute. First you're going to substitute s equal 2. When you substitute s equal 2, you can see that you get 11 on this side, the other side is you get b, so b equal 11. So you can get the b value directly. And to get the a value, what you can do is you can actually plug in a smart value here. So because you can see that you can plug in 2 again, but what we're trying to do is we try to plug in smart value. The goal is see whether you can make this term 1. If you can make this term 1, then you can get a directly. So what we're going to do, we're going to plug in s equal 3. So let's plug in s equal 3. Substitute s equal 3. So when you substitute s equal 3, what happened? On the left side you get 21 because it is 9 times 2 plus 3 is 21, and if you plug in 3 you get 2, and then a we don't know, b already we know that's 11, so this can give you the value of a. So you can see value of a is 8, and you can see these two values match the two previous values. So that's like how you can find it using the partial fractions. Okay, so let's look at another example. So let's look at the next one. So let's say we have s plus 7 over s plus 2 s minus 1 squared, and we can, this is like a regular partial fraction problem. So we write this one term by term. So the first one is a over s plus 2, and then the second one is a repetition. So we start with the smallest one, which is s minus 1 b, and the rest of the terms follow the same pattern. That means s minus 1 squared is also follow the same pattern. So it's a c. So goal is to find ABC, and then standard technique. So we're going to multiply by the denominator term on the left side, the whole expression. So you get s plus 7 identical to a, and then what happened here is you're going to cancel this plus 2 term and write the rest. So it is s minus 1 squared for the first one. Second one, you only cancel one of the s minus 1, so you get s plus 2 and one of the s minus 1. And this last one, c, you cancel the whole s minus 2 squared term, so you only get s plus 2. Okay, and then you can see you can use a substitution to find two terms, just two terms. So let's do that first. We use what they call the hybrid method for this one. So we do the substitution as much as you can first, and then go for the coefficients. That's the quickest way to get the answer. So we're going to go with the substitution. So we're going to substitute to find, let's say you're going to find a. You're going to find a, see whether there's a common term. Yes, there's a common term. So you can try to make that term 0. So that means you're going to substitute s equal -2. So when you do that, you get 5 on this side. This is a. If you plug in -2, -2, -1 squared, which is going to be 9, and then all the terms are 0, it's going to give you a. So a is 5 over 9. And then let's try to find b, and you can see you cannot find b using a substitution because there's no common value on the other two terms, so you cannot find b. but you can find C. So we're going to go to the C. So when you find C, you can see if you look at the, S minus 1 is there. So we're going to apply in S equal 1. So we're going to apply in S equal 1. So substitute S equal 1. So when you do that, you get 8 on this side. And C, you plug in 1, you get S plus 3. So you get S plus 2, you get 3. So this is going to give you C value, which is 8/3. Now the question is how to find B. So to find B, you can plug in just some other value. If you just plug in any other value other than -2 and 1, you can find B from this one, because you just get equation and solve it and get the value. But there's like an easy way. What's the easy way? This is not an equation, this is an identity. That's why this has to be an identity. Since it's an identity, the coefficients of both sides should match to each other. So we can use that property here. So we can say we're going to match the coefficients of the largest term, that means S squared. So there's no S squared term on this side, so 0. But you can see when you distribute the first term, which is S squared minus 2s plus 1, and there is a squared term. So the squared term, so that means the coefficient has to be a in this case, because when you have squared, you multiply by a, so a. And then also you can see there's a squared term coming from these two, so that means the coefficient is b. And you can see that there are no more squared terms, so that means this is going to give you b, so b has to be just the negative of a, so that means negative 5, 9. So that is the easiest way to find the 3 coefficients in a situation like that. Because if you just do it like that, it doesn't take much time. But this is a special technique. So we do the substitution as much as you can, and then use the coefficient start with the highest power. This is what we normally call the hybrid method. So we use the hybrid method for this one. Hybrid method. So use the coefficient, we use the substitution first, and then the coefficients. And if you have one more, we just keep going. Then we're going to go with the coefficient of s. But we in this case we don't have to. Okay, so let's go to the next problem. Actually, before we go to the next problem, I would like to discuss another technique to find this value. So another technique. So we can use the cover-up method and something else. So let's see how we can use that. So second method. So we start with the same expression. Then what we can do, actually you can find A and B using the cover-up method. A, not A and B, A and C. The largest terms you can always find using the cover-up method. So let's see. So for the A, so what we can do is, so you're going to cancel S plus 2. So you're going to get A like this. So here is plus 7, and you only ignore S plus 2 term. You cover up S plus 2 term and plug in the 0, which is -2. So you get 5 over a -3 squared, which is 5/9. That's exactly what we get earlier. We can also find C like that. So C is, if you cover up S minus 2 squared term, you're going to get, so S plus 7 or S plus 2, and evaluate it at S equal 1. So when you do that, you get 8 over 3. And you can see those two numbers actually match. Now the question is, how we can find B? So you can use the cover-up method for B, but what we can do something interesting. What we're gonna do, we try to make this term equal to 1. We just try to make this equal to 1. So that means, so then you get B directly. So what we do, we're gonna plug in S equal 2 to the whole expression. So let's substitute S equal 2. So when you do that, and you can see on the left side, you get 9 divided by 4, and on the other term we already know what's the value of A, so let's plug in that. So it is 5/9, and when you plug in C equal 2, so you get 1/4, and then B, that's what we are looking for, and then 8/3. Now what we're going to do is we're going to solve for B. Okay, so if you solve for B, it's going to give you B equal, just like algebra problem after that, 5/9. So that's like another way to do it. So use the cover-up method to find the A and C. to find the other value, just plug in some other value, but what we try to do, we try to make the bottom equal to 1. So because it simplifies well when you do that. So we plug in s equal to, so when s equal to, you get the value of b. So that's like another technique to find this ABC. Okay, so okay, I have never seen this one anywhere, like this argument, this trick here. Okay, so let's look at several special cases now, special situations. So special case of problem number 13. So let's say we have s plus 7 over s squared minus 4. Normally, like if you get a problem like that, what we normally do, we're gonna break this as s minus 2 and s plus 2 and find the partial fractions. But when you do the Laplace transform, inverse Laplace transform, we don't want to do that. We already have the answer right here. So what we just split this. We can write this one as s over s squared minus 4 plus 7 over s squared minus 4. That's the first step. We split them into 2. And then now let's see how we can write the inverse transform, because we know that the sine and cosine, actually in this case the hyperbolic sine and hyperbolic cosine. So these are the identities that we have. And we know these two results. We know the Laplace transform of hyperbolic cosine, cos omega t is equal to s over s squared minus omega squared, and Laplace transform of sin omega t, which is omega over omega squared minus. So what we try to do, we try to bring it to this form. So only thing that we need to worry about is this special omega going there, the square root of this term. So we're going to recreate that. So because of that, so I'm going to do this inverse Laplace transform problem here. So it's a L inverse. So we have s plus 7 over s squared minus 4, which is equals to inverse Laplace transform of s over s squared minus 4. And here what we're going to make some adjustments. So you can see the special number that you need. So which is s squared minus 4. So the special number, so we know that the 4 is 2 squared. That means the special number that we need to the top is 2. So what we do, we divide by 2 and multiply by 2. So you put the 2 inside and 2 put outside. But outside has to be 1/2 to cancel each other. And then we put the 7 here. That's the 7 you had. So now we can write the inverse. So we can write the answer. That means going to be, this is cos 2t, where 2 is the omega in this case, and then plus 7/2 sin 2t. So you can write it like that. So that's the idea. And you can see this is different from the regular partial fraction method. So we did not write the partial fractions for this one. We can directly write the answer using hyperbolic functions. Okay, but you can still do it, and then but it's just a wasting time because we already have the answer right there. Okay, so let's do another example. Actually, before doing another example, let's see what exactly happen if you do that. If you try to find the partial fractions, what exactly happen? So let's look at that. So here's plus 7 squared minus 4, and then you can see that the factor size minus 2 and is plus 2. So that means your partial fraction going to be identical to a over one of them and the other one. And you can see you can use the cover-up method for this one. So you're going to get a and b like this, and b. Now we can plug in those values. So we can write this one as L inverse s plus 7 over s squared minus 4. So we can write this one as the coefficient 9/4. I'm going to pull it out, and then you can have L inverse. So what you get is 1 over s minus 2, and then plus, and the minus again, 5/4 L inverse 1 over s plus 2. So what happened now? We can find them. So we can see this is simply 9/4 e to the 2t that's the inverse of 1 over s minus 2 e to the 2t, because we know this identity. So we know that if we have the Laplace transform of e to the minus at is going to be 1 over s plus a. So that's what we use. And then, or if you change the sign, so if you want to write e at is opposite sign, it's going to be 1 over s minus a. So it's the same thing, just opposite sign. So because of that you get that, and similarly you can get this one as 5/4. You have 5/4 e to the minus 2t. Now what we can do, we can plug in for these two from using the hyperbolic functions. So if you have the hyperbolic function, you can plug into those two expressions. So what you get is, it is simply 9/4, and we know that e to the 2t actually equals to cos 2t plus sin 2t. That's the e to the 2t. And similarly you can plug in for the other one, 5/4. That's going to be cos 2t minus sin 2t. Now what to do the algebra and simplify, and when you do that you can see that you exactly get the same answer. You can get cos 2t plus 7/2 sin 2t. So you will get the same answer even with this method, but it's a little long, because you could have got the answer much earlier, much quicker if using the other technique. Okay, so let's look at the next one. So let's look at a very special problem, and that we normally don't do in the regular partial fraction method. So we have the next problem, which is question 13. I'm going to call it 13 star because it's a very special problem. So we have this. So we have s plus 7 over, let's say, s plus 1 and s squared minus 4. So if you get a problem like that, what we normally do, we're going to completely factor the bottom, but in Laplace transform technique we are not going to do that. So this problem is especially different from other problems. So what we normally do, we leave it like that. So that is the difference between regular technique and this technique. So we write the standard way, a over s plus 1, and for the other term we leave it like that. We do not factor. We write it s squared minus 4. So it's a degree 2. That means this has to be degree 1. So the bs plus c. So the goal is to find a, b, c, and then after that we know this is like a regular problem. So we're going to multiply by both sides, so you're going to get s plus 7 identical to a. So you get s squared minus 4 here plus bs plus c. You get s plus 1, and then we're going to use the hybrid technique. So we're going to go with the substitution as much as we can. So we're going to say, we're going to substitute s equal -1. So when you do that, you get 6 equal a. If you plug in -1, you get 1 minus 4 on this side. So that's going to give you the value of a, so which is 6 divided by -3, so which is -2. So we use the hybrid technique. So we're going to go with the coefficient technique now. So we're going to go with the highest coefficient, so which is s squared, and you can see there's no s squared term on this side, so it is 0. And you can see you get a s squared from this and also from that. So that means the coefficients are a from the first one, b from the second one, and that's it. That means you can find b, which is just the negative of a, so which is 2. So we already know 2. Only thing that we don't need to find is c. So we go for the next lower coefficient, so which is the coefficient of s. So if you go for that, you can see the 1 on this side, and there's no s term from the first one, but from the second one you can see you get s term if you multiply bs and 1, so that the coefficient is b. And also you get another one if you multiply c and s. So the coefficient is c. So if you plug in the value of b, so c is equals to 1 minus b, so which is going to give you -1. So that's what you get as the fractions, as the coefficients. So we can write it like this now. So we have this after you plug in the values, but what we normally do is we can when you do the inverse Laplace transform, we can split this term and we can write it like this. So you can write this as 2 over s plus 1, and then the next one you pull the 2 out, you write this one as s over s squared minus 4, and then next one you pull the minus 1 out, you write this one as 1 over s squared minus 4, and then you can see that it's very easy to find the inverse now, term by term. Okay, so but we do that in in the inverse Laplace transform video. We're gonna do that. We're gonna do like a couple of examples, and this will be one of the examples, and how to find the inverse of this. So we talk about that again there. Okay, and you can find the link in the description. Okay, so why don't you try this as an exercise? So try to do this one on your own. So what happens if we have s plus 7 over s plus 1, and then we have s squared minus 3, and you can clearly see that in this case it will be very difficult if you try to do the standard way. What's the standard way? We're going to factor the bottom as s minus square root 3, s plus square root 3, and the algebra would be very difficult if you don't do that, especially with square root terms. So this would be the best way to do it. Okay, but why don't you try this one? Okay, so let's look at the next one. Let's talk about the other type. So first type, what we with just the division. Next we talk about the different linear factors, and then third we talk about repeated linear factors. Now let's talk about what we have when we have the quadratic factors. So what we normally call quadratic factors, but normally like irreducible quadratic factors. Those are irreducible. So why we worry about the irreducible part? So let's say you have something like this, s plus 7 over s squared minus s minus 6. But if you have something like that, and you know that clearly you can factor the bottom, so you can write this one as s minus 3 and s plus 2, so that you can break it down. So you can write this one as so s plus 7, better write like that. So let's say this is equal to s plus 7 over s minus 3 and s plus 2. So you can break it down now. So you can write this one as identical to a over s minus 3 and the b over s plus 2. And then we can find a and b using cover-up method or any other technique. So, but that's not the issue. Let's look at this problem. So when you look at this problem, s plus 7 over s minus 1, s squared plus 4, you can see this problem is different from other problems. The reason is this is irreducible. This one is irreducible because you cannot break it to two linear factors with real coefficients. So this is what we normally call irreducible one. So if it is an irreducible one, what we normally do, this is like similar to the previous problem that we did. So we can write this one as a over the linear factor s minus 1 plus, here the bottom is s squared plus 4. You can break this one, so it has to be bs plus c. So this will be very similar to the problem 13. So we use a standard procedure. So we're going to multiply both sides by the denominator term. So you get a equal a times s squared plus 4 plus bs plus c times s minus 1, like a standard problem. So we do the substitution and the coefficient techniques. So then we're gonna get these. So you get a as 8/5. Now we go with the coefficient technique with the largest coefficient. Then go for the next coefficient, the coefficient of s. So you get c as -3/5. Now we're gonna plug in the values and we can write it like this. then. So we can plug in the value, and then we can also split these two terms, and then we get three terms like that. So the first one, if you look at the inverse, first one is going to give you the e to the t term, second one is going to give you the cosine term, the third term going to give you the sine term. And it will be clear when you do the problem in the inverse Laplace transform video. So this will be a problem there. So you can you know, like how to find the partial fraction, this one. Okay, let's look at one more. Let's look at a different type now. So what happens if you have two irreducible quadratic in the bottom? So let's look at this one. Suppose we have 12 divided by a squared plus 1 and a squared plus 4. And you see that both of them are irreducible. So how to do it? So we can write the same argument as before. So we can write this one as first it is a squared plus 1. That means the numerator has to be as plus b. That's the first one. The second one also, it is a squared plus 4, and it's also irreducible, so it has to be cs plus d. So that's what you get. Now we're going to use the standard argument here. So we're going to multiply by the denominator on the left side. So you get 12 equal, we have as plus b times the other one, which is a squared plus 4, and the other one is cs plus d, and you get a squared plus 1. So that's the identity you get. This has to be identity. These are not equal signs. These are identities, because we're going to use the property of identity. If it is an identity, then only you can equate the coefficients on the two sides. If it's an equation, you cannot. Okay, so that's like a theoretical need. So now what we do, we start with the highest power and go down one by one. So we start with the highest power, which is the coefficient of s cube. So there's no s cube term here, but you can see that there's a s cube term. If you multiply first two terms, you get a s cube term. So that means the coefficients are a plus c. That's the only coefficient. There are no other way you get s cube. So let's go to the next one. So which is the coefficient of s squared. So we start the highest power always. And again, there are no squared term here. Now let's think about how to get a squared term. You can see you get a squared term if you multiply b squared and d squared. That means it is b plus d. So let's go to the next one, which is the coefficient of s. So how to get s term? Again, no s term. And you can see you get s term if you multiply first and the last, and the first and the last. So that means the coefficient has to be 4a plus c. And then we go with the last one, which is the constant term. So you can see the constant term. So the constant term going to give you 12 on this side, and on the other side you get 4b and a d. So that's what you get, 4b plus d. Now the thing is that we have four equations. How to solve them? So we can use a special technique to solve them. So what we're going to do, we're going to subtract method for this one. So if you look at the first and the third one, if you look at the first and third one, and if you subtract the first one from the third one, you can see if you subtract the first one from the third one, what happened? You get 3a. You get 3a equal 0. So this says that a equals 0. And if you plug in that value to the first equation, you can see that c equals 0. So you quickly find a and c. So that's the argument. So what we did, we subtract first equation from the third equation. So we did 3 minus 1. That's going to give you this. And the same thing, so let's do now, if you look at 2 and 4, equation 2 and 4, you can see you subtract them. So when you subtract, you can see the d get cancelled out. So you're gonna get so again. So what we did here is 4 minus 2. So when you do that, and you can see you get 12 equal. You get 12 equal 3b, and this is going to give you the b value. So b equal 4, because 12 for the b equal 4. And then if you plug in that value to the equation 2, you can see d equal negative b. So that means negative 4. So we can easily find all those 4 values if you use this technique. You can just a subtraction. Subtract and you get the answer. Now let's plug in the value, and then we're gonna get this. And then after that, you can see that you can easily invert these two, because both of they are all both sine functions. And then you can try this one. So why don't you try this problem and see what numbers you get. And you also notice something special here. You can see the original problem has a 12, which is a constant, and you can see the A and C get cancelled out, and you only get B and D. So now let's see what happened. The numerator has a S term. So we have S over S squared plus 1, S squared plus 4. So it's very similar, but the only thing is you have S in there. So again, same argument. So we can write this one as AS plus B over S squared plus 1, and then CS plus D over S squared plus 4, and then same argument. So we have S equal AS plus B, the other one, and then CS plus D, the other one. So we can use the coefficient technique, because you can substitute anything here. So we're going to get these 4 equations, and then we do coefficient of S. Then we do the constant term. Then as before, we use the subtraction technique. So we're going to go with the first and the third. So when you subtract the first from the third, and you can see you're going to get 1 equal 3a. So which is going to give you a equal 1/3. And then if you look at the first equation, that's going to give you c equal negative 1/3. So we know a and c, and do the same thing. We can subtract 2 from 4. So when you do that, d get cancelled out, and you can get 0 equal 3b. It's going to give you b equals 0. So if b equals 0, if you look at the question number 2, you can see d equals 0. So now what happened? B and D are 0. So you get B and D 0. So then we can plug in the value. So you will get this as the equation. And so this is what you get. And you can see that if you do the inverse, this is a cosine. This is also cosine. So you get cosine, cosine this time. So in the previous problem, you get sine, sine. So now let's see what happened if you have both of them. If you have a S term and a constant. So this is the next one, problem number 17. So we have S plus 3 over the same denominator. So as before, we have this, and then we get this. Now we can write 4 equations for the 4 unknown. So we get these 4 equations, and we're going to solve them as before by subtracting. And the other two also going to give you this. And then we can plug in these values and split them into 4 different factors like this. So you get 4 terms like this. So we split them, and also you can see that we put a 2 and a negative 2.5, because 4 is 2 squared, and you can easily invert. Okay, so now when you invert, this is what you get. So the first term going to give you 1/3, cosine t. The second term going to give you sine t. Third term going to give you 1/3 cosine 2t. The third one is going to give you 1/2 sine 2t. So these are the four terms you get from this one when you do the inverse Laplace transform. I mean, that's the whole idea. So as a problem, it's not like that bad, but there are special techniques how to solve them. So that's what you need to remember. Okay, so let's look at another special case. So as the next one, let's look at this special problem. So let's say we have s over s to the 4th power minus 4, like that. And so this is like a special problem. So you notice that you can write the denominator as s squared squared minus 2 squared. So then we can use the differential squares and we can write this one like this. So we can write this one as s over s squared minus 2 and then s squared plus 2. Because of that, we can write the partial fractions. So we have one with s squared minus 2 and we have another with s squared plus 2. So you can write this one as as plus b and this one is cs plus d. So again, as before, we write the four equations. So this can lead to s identical to as plus b s squared plus 2 and the other one is cs plus d to s squared minus 2. So we're gonna write the four equations as before now. So we get these four equations and you will notice that we cannot use the technique that we used earlier directly, because last time we just subtract equation 1 from equation 3. But this time we cannot do that. The reason is you can see there's a different coefficient in front. So we do a slightly different one. What we're going to do, we're going to multiply the first equation by 2 and then we subtract. So what we can do is we can say, actually in this case you can add them. So we can write this one as 2 times equation 1. So it is 2 times equation 1 plus equation 3. So when you do that, you can see you get 1 equal 4a. 1 equal 4a, and this is going to give you a, so which is 1/4. And then if you use equation 1, this is going to give you c, which is negative 1/4. So we found a and c. So similarly, if you look at the equation 2 and 4, you're going to multiply the equation 2 by 2 and add to equation 4. So we do 2 times equation 2 add to equation 4. So when you do that, and you're going to get 0 equal 4b, and this is going to give you b equals 0, and because of that d equals 0. Okay, so that's what you get, and then we're going to plug in the values and we can split them and write it like this. And then you can clearly see that the first one is a hyperbolic cosine and the second one is hyperbolic regular cosine. Hyperbolic cosine, regular cosine. So you get the answer like this. So if you invert, you get this. 1/4 cos square root 2t minus 1/4 cos square root 2t. So one is a hyperbolic cosine, the other one is a regular cosine. Okay, so let's look at maybe just 2 more problems with again different types. So we would like to do one with the direct delta function. Let's do one with the direct delta function now. Say we have this is like a special problem, so I will start here. let's say we have 6x to the fourth power divided by s squared plus 2 s squared minus 3. So what happened when you multiply these two, you can see that you get a s to the fourth power. When you divide 6x to the fourth power by s to the fourth power, you can see you are going to get a 6. So the first term is 6 plus the rest of the term has a regular argument. So this is going to be s squared plus 2 times a plus b, and then from the other one we have s squared minus 3, so we have cs plus d, and then as before, so we have 6s to the fourth power. Actually we need more space, so let's write it like this. So now we're gonna go with the equating coefficients. We're gonna start with the largest power, and you can see there's no point writing x to the fourth because we already have the 6 there, so we are not gonna write that. So we're gonna go with the next one, so we're gonna start with the cube. So we get these three equations and we're gonna solve them as before. So again, consider the first and the third one. If you multiply the first one by 3 and add to the third one, we get this. When you do that, you get 5c equals 0. So this says that c equals 0, and then equation 1 says a equals 0. So we're done with the first two, and then same with the second and the fourth. And what you can do is you can multiply the first one by 3 and add it to the fourth one. So you get 5d equal 54. So this is that d equal 54 over 5, and from that you can find b. So b equal, you get 6 minus d, and if you simplify you're gonna get negative 24/5. Okay, so that's gonna give you all the a, b, c, d values, and then we can plug in them and we get this. And then after you plug in, this is what you get. And then now you can see that we have this special function. What is the L inverse of 1? And we know that that's a direct delta function. So we can write this as 6 delta t. That's the direct delta function. And the next one is, you can see it is 12 square root 2 over 5. The next one is the sine, so which is sine square root 2t, and the next one is 18 square root 3 over 5, and because of the negative sign, this is the shin. This is going to be shin hyperbolic sine square root 3 t. So that is the inverse of this one. So yeah, so first one is the direct delta function, next one is the sine, third one is the shin. Okay, so let's do one last problem of a different type. So so let's do this one. So last problem. So how about you have something like this? Suppose we have I'm going to put a star here because it's like a very special problem. So we have s plus 1 over 2s squared minus 4s plus 3, and clearly you can see that you cannot factor the denominator, so you cannot factor that because there's a negative discriminant. So what you do in this case, we're going to use the completing square technique. So use the completing square technique. So to do that, you notice that there's a 2 here. So what we're going to do, we're going to manipulate that first. So you're going to pull 1/2 out first. So when you pull 1/2 out, and actually let's write it like this. So we have the numerator, we leave it like that for the moment, and then we take 2 from the denominator. So when you pull 2 out, so you can see you get s squared minus 2s minus 2s, again minus 2s, and then we leave a space there, and plus 3. Now what you're gonna do, we're gonna need to know what is the special term that we need to add to make this one is a complete square. So that's the whole point. So what we normally do is we take the half of this coefficient and square that. That's the term we're gonna add. So you can see when you take the half of that, which is -1, when you square, you see that the special term that you want to add is +1. But when you add +1, because of the 2, you are actually adding a 2. So to cancel that, you subtract 2. So it's like a add 2, subtract 2 situation. That's what you get. So if you simplify this a little bit, so you're going to get s plus 1 over 2. And then you know that because of special addition, this is going to be s minus 1 squared plus 1. So that's what you get after the completing square. Now what we're going to do is we're going to pull the 1/2 out now. So we're going to say 1/2 out. If you take 1/2 out, you're going to get s plus 1 over s minus 1 squared 1/2. So you get that. Now what we're going to do, we're going to split them into two terms. So we can split them into two terms and we can write it like this. I'm going to write it here. So you can see 1/2. And then you also try to recreate this term in the numerator. So what are you going to do? You can write this one as s minus 1, not just s, but s minus 1 because of the denominator term, and s minus 1 squared plus 1/2, you can leave it like that, plus because of this minus 1, you need to add extra 1 to cancel that out, so that means it's going to be 2. So it's a 2, and then here we have s minus 1 squared plus 1/2. And now actually we can easily invert this using the first shifting property like this one. So if we use this one, then we can write the final answer like this. So you can see the first one is the cosine, the second one is a sine, and you will see that there's a s minus 1 term there. So that's the reason why we have an e to the t term in both of them. And the first one is a cosine, the second one is a sine. And the reason why we have square root 2 is you can write this one as 1 over square root 2 to the square. Okay, so that's what you do in a problem like that. You're going to rewrite it like that and you split them and you get one cosine and one sine. If there's a negative sign, you will get hyperbolic sine and cosine. Okay, so you can try these three problems and see whether you can invert them. Now use a similar technique to answer these questions. So first use the completing square of the bottom term and then use that to find the inverse Laplace transform of these three functions. So you can put the answer in the description, answer in the comment section. Thank you for watching.